All right, so we're in section 15.7. All right, so what I want to do with the divergence theorem is relate it back to something we talked about with Green's theorem. So in section 15.4, we talked about in the plane, we came up with, or we stated Green's theorem. Green's theorem says that the line integral around a closed curve of f dot dr was the double integral over the region bounded by the region that the curve encloses of dn dx minus dm dy dA, where our vector field f was mi plus nj. So this was Green's theorem. And we did a little work with Green's theorem, and we found the line integral of the normal component of the field around this curve. And we did some work, and we did some manipulation, and we came up with that the integral around our closed curve of f dot n, the normal component of f around this closed curve, was equal to the double integral over the region of the divergence of f in the region. So we're saying that the integral of the outward component of f, normal component around the curve, around the boundary of a region, is equal to the double integral of the divergence of the field over the region. And this was in the plane. We did this right at the end of section 15.4. Yeah, it was we went through a long derivation, and at the end we said all of that work was for this. Okay. Remember that?
I can't remember.
All right, and it was a while back. So we're saying that the line integral around the boundary of our normal component of f is a double integral of the divergence of f over the region bounded by the curve. So what we're going to do with the divergence theorem is really just an extension of this idea basically into 3 dimensions. It's exact same idea. What we're going to do is take the double integral over the surface integral of the normal component of f over the surface, and it equates to a triple integral of the divergence in the solid bounded by that surface. So let's write the divergence theorem. Divergence theorem is an extension of this idea. So the divergence theorem tells us that the surface integral over a surface of f dot n ds, the normal component over that surface, is equal to the triple integral over the solid bounded by the surface of the divergence of f dv. So D is a solid region. And is bounded by a closed surface And it's important that we're talking about a closed surface here. And N is the outward unit normal vector. So what the divergence theorem says is that if we sum the outward component of F over our closed surface, that is equal to the divergence of F over the volume enclosed by that surface.
Is that first integral, is that the flux?
This is a flux integral. So we're saying that the flux through the surface is equal to the divergence in the volume of the solid. So this is the divergence theorem. The way we'll usually use divergence theorem is if you've done much of the work from the surface integral section when we talked about surface integrals and vector fields, when we talked about flux integrals, there's a lot of work to doing those. We have to find our unit normal vector. We have to take our dot product. We have to do the double integral over our surface. Triple integrals are usually fairly easy. We have a solid region. We just project that onto our coordinate planes and find our boundaries, find our limits of integration. So triple integrals usually a little easier to evaluate than double integrals, than surface integrals. The divergence theorem, also called, sometimes you'll hear it called Ostrogradsky's theorem. And he was a mathematician, the first person that published the divergence theorem, Russian mathematician. And he was denied a degree in Russia because he was an atheist. So they denied him a degree, so he couldn't really be like he wasn't officially a scientist. And you also see it called Gauss's theorem. Gauss proved it first, but he didn't publish it until later. So Ostrogradsky proved it first, published it first. Gauss proved it first, but didn't publish it. You'll usually hear it called the divergence theorem or Gauss's theorem. Proof is not complicated, but it's long, and there are lots of details that you have to take into account. The book does a pretty good job of going through the proof. So I'm not going to do the proof of the divergence theorem. So any questions on what the divergence theorem is? All right, let's look at a couple of examples of how we're going to use the divergence theorem, or an example of how we're going to use the divergence theorem. And then I want to finally talk about a physical interpretation of the divergence. So we want to evaluate this flux integral. And a couple of important things to keep in mind when we're using the divergence theorem: our surface has to enclose an entire region. It has to be a closed surface to use the divergence theorem. So we've done surface integrals where we don't have a closed surface. We had a plane or something like that that's not necessarily closed. To use the divergence theorem, your surface has to be closed. And sometimes the notation you'll see for that, for a closed surface, would be this. So a little circle tells us we have a closed surface. The other way that you'll see this problem stated is we want to find the outward flux. Of F through S. So that's the other way the problem could be stated. So we want to find the outward flux of F. And we want to use a divergence theorem. Our field F is x, y, I hat plus y, z, j hat minus y, z, k hat. And our surface is z equals the square root of a squared minus x squared minus y squared, and z equals 0. So those are the boundaries of our surface. So what is this? What is this? What is our region? What is the surface? A hemisphere, right? So the bottom boundary of our surface is the xy plane, and the top boundary is this sphere, x squared plus y squared equals z squared equals a squared. So I'm just going to rewrite that. X squared plus y squared plus z squared equals a squared. So that's our boundary. So if we think of our surface integral, to evaluate this as a surface integral, this flux integral, we would have to do we'd have to do two separate integrals. We'd have to do one flux integral through the bottom through z equals 0. So our outward unit normal vector is negative k hat, and we would have to evaluate the surface integral, the flux integral through that portion of the surface, and we'd have to evaluate the surface integral through the upper portion because our outward unit normal vector is different on that portion. If we remember, we would express our surface as z minus the square root of a squared minus x squared minus y squared. Find the gradient to find our unit normal vector. Do f dot del g and integrate that over our region. So that there's a lot of work involved there. So we're going to use a divergence theorem. So before we even set anything up, what are we going to choose for our coordinate system? Spherical. It's a sphere. So we have this upper hemisphere. Radius is a. We're going to use spherical coordinates. And we finally get back to our triple integrals that we talked about in chapter 14. So what if I represent this surface in spherical coordinates?
Rho equals A.
Rho equals A. And what about z? Remember what an upper hemisphere comes out to be in. Well, do we even need to worry about that? I don't think we need to even worry about that. So we know that our sphere is rho equals A. So we are going to use the divergence theorem. We just need to take the triple integral of the divergence of f over our region. So let's find the divergence of f. Divergence is del dot f. Divergence of f is going to be nice and easy. Y plus z minus y, which is just z. And in spherical coordinates, z equals rho cosine phi. So there's z. There's our integrand is just z.
Is this on the note sheet?
I'm not sure. I would have to look. So the divergence theorem tells us that our double integral over our surface of f dot n ds is a triple integral over our region of del dot f dv. Well, here's del dot f. So our integral theta from 0 to 2 pi, phi from 0 to pi halves, upper hemisphere, rho equals 0 to a, nice easy limits. Z is rho cosine phi, so I have rho cosine phi. So phi is from the positive z-axis down, then we'll rotate around. What's that? Oh, yeah, not theta, thank you. And then our dv in spherical coordinates, rho squared sine phi, d rho, d phi, d theta. So a nice, easy integral to evaluate. Our rho integral is just rho cubed. Our phi integral is just sine phi. And then our theta integral is just d theta. So this is a nice, easy one to evaluate. When I evaluate this all out, I get pi a to the 4th over 4. So this tells us that the divergence of the field, the flux of the field through this surface is pi a to the 4th over 4 units. And this is much easier than evaluating, I think, the two double integrals, the two surface integrals that we would have had to evaluate. So that's how you're normally going to use a divergence theorem, is to simplify evaluating a flux integral on a closed surface. And one way that I think of, that I kind of visualize the divergence theorem, is if we think of flux as our field flowing through something, on the interior of the solid, if we think of dividing the solid into tiny little pieces, if we have a flux through a little piece of volume, it's going to go in one side and out the other on the interior. And all the way through the interior, it's going to go in one little piece of the volume and out the other if we have these tiny little pieces of volume. So we're thinking of flux as our field flowing. Flows in, out, until you get to the surface, and then it can only go out. So we're taking that normal component. So anywhere inside if we sum the divergence on the interior, we get all of it going in, going out, going in, going out until we get to the surface, and then it finally goes out. So that's one way that I picture the way the divergence theorem works. Is on the interior, we have the flux going through our little piece of volume, and finally that has to equal what goes out of the surface. All right, so questions on that example. And again, like we talked about with Green's theorem, and like we talked about with the fundamental theorem of line integrals, this is an extension of the fundamental theorem of calculus. We're saying that we are integrating this quantity on a region, on some space, and that integral equals some other quantity evaluated on the boundary of our region. So on the x-axis, when we integrated our function, we took the function at the endpoint to the integral of the antiderivative at the endpoint, and subtracted the antiderivative at the beginning point. Here we're integrating the divergence over the interior of our region, and that equals this thing on the boundary of the region, something evaluated on the boundary of the region. So this is a generalization of the fundamental theorem of calculus, just like Green's theorem was, and just like the fundamental theorem of line integrals was. And it turns out, when we talk about it tomorrow, Stokes' theorem is another kind of extension of the fundamental theorem of calculus. All right, I want to talk quickly about a physical interpretation of the divergence. Because divergence was one of the first quantities that we calculated at the beginning of the chapter. In 15.1, we talked about how you calculate the divergence of a vector field. And we kind of hinted about what the divergence was, but we said we needed to do some more work before we could really interpret it. So we just talked about the divergence theorem. Divergence theorem tells us this flux integral over a closed surface is the integral over the solid bounded by that surface of the divergence of F. And the way we denote a closed solid region, you'll also see a circle around your triple end. So this says the flux through the surface is the divergence over the volume. All right, so we're going to visualize a tiny surface. The flux through that surface, so we're talking about just a very, very tiny piece. The flux through the surface is approximately del dot F delta V. So we're talking about a tiny, tiny little piece of surface and a tiny little piece of volume. So delta V is the volume of our tiny little closed surface. So we could say the flux equals the del dot F delta V. I'm going to just divide both sides by delta V. So flux over delta V is del dot F. And then if we let delta V become very, very, very small, our tiny closed surface gets smaller and smaller and smaller, we take the limit as delta V gets very, very small. We have that del dot F, the divergence, equals the flux per unit volume. So that's our physical interpretation of the flux, or of the divergence. The divergence tells us the flux per unit volume at a point. So if we're thinking of flux as being an outward flow, the divergence tells us the outward flow per unit volume at a point. So that's a physical interpretation of what the flux is. The flux out of a solid, right? Is the divergence is the flux per unit volume. Like an electric field. So if you have a charge enclosed by a surface, the flux of the electric field is the divergence is the flux per unit volume of that electric field. How much electric field is flowing out of a volume per unit volume. So that's a physical interpretation of the flux, the outward flow per unit volume. And you'll see the flux, these kinds of integrals do show up in electromagnetism, in Maxwell's equations for electromagnetism. They're full of these quantities that we've been working with, the flux, the curl, that kind of thing. And if you extend that a little bit, what Maxwell's equations tell us, if you extend that a little bit, stretch it a little bit, then you get the language of general relativity. And it's very similar to what we're doing with vectors here. So these ideas are really, really powerful, really important, and give us a lot of information. So if we think of the divergence as the flux per unit volume at a point, we can classify a field by the sign of the divergence. So if our divergence, you'll see this if you ever do fluid mechanics, if del dot F, if the divergence is greater than 0, we call F is a source. So the divergence is positive, so we're thinking of the field flowing outward. So F is a source. If del dot F is less than 0, we call the field a sink. So the field is sinking into the volume. It's absorbing. We can think of it as absorbing, something like that. And if del dot F, if our gradient is 0, we call F incompressible. So the field's not flowing at all. We call it incompressible. Yes?
Would the sink like become the charge outflow flow, or like the flux is flowing into that
Right,
out?
right. And you'll see if you, in the flux is used a lot in fluid mechanics. So you talk about how a fluid is flowing, and you talk about fluid flowing through a surface. So if the fluid is going into some region, that region is a sink, or that field would be a sink because the fluid, the velocity field is going into that region. All right. Questions on the divergence theorem? So really the divergence theorem gives us a way to evaluate flux integrals by using a triple integral, a volume integral. And to me, the really cool thing about the divergence theorem is this relationship between the boundary of a region and the interior of a region, which is really the same as what we talked about in Calculus 1 to evaluate a definite integral on a piece of the x-axis. All right, we'll talk about Stokes' theorem tomorrow.